Swayam Prabha. Digital India. Educated India.
Let us now look at review of theory of elasticity. What is the fundamental difference between theory of elasticity and strength of materials? In theory of elasticity, no prior assumption on displacement is usually imposed. What we did in strength of materials? We imposed plane sections remain plane before and after loading. With that kind of an assumption, for a class of slender members, we were able to arrive at the stress fields. In fact, if I take a circular disc like this, you cannot solve it from strength of materials approach. In fact, you need to go to theory of elasticity, because in this, because of the diametral compression, plane sections do not remain plane before and after loading. So, you have to necessarily go for theory of elasticity, and fortunately from theory of elasticity it is possible for us to find out a closed form expression. That means, if you specify x y, you will get this kind of value for all points in the domain except the load application points. And you should also recognize, once you come to theory of elasticity, you will classify the objects as simply connected and multiply connected. This is a simply connected object, though in general you do not impose the displacement. You may try to use experimental information on displacement as part of your solution approach. In fact, this is invoked in the case of torsion of rectangular cross section. I need a volunteer to come and take the specimen and then twist it. It is a rectangular shaft and this is being twisted. You have lines drawn. After it is twisted, you find these lines become curved. In fact, there is a projection in the axis of the shaft. If you take that as a z axis, you have a projection here, and if you look at very closely, these lines are similar when z is varied. So, what you gain is, there is warping, and you say this warping is function of only the cross section, whatever the cross sectional plane, it is same as every section of z. You use this as a basis to solve this problem. In fact, when we look at solution of stress field for the case of mode 3, we would go through this displacement formulation. We would take this kind of an approach and evaluate the stress field. And once you come to multiply connected bodies, you have to invoke uniqueness of displacement. And what are multiply connected bodies? Suppose I take a ring like this. What you have here is, I have a hole in between. In fact, you have solved this as a Lame's problem. You have internal pressure and this is a thick cylinder. So, you can find out what are the stresses developed because of internal pressure. In fact, if you go and look at the way that you have solved this solution, you would have made one of the coefficients defining the problem to go to 0, mainly because when I go through this complete circle once, you want to have at any cross section the displacement remains same, in order to ensure that you make one of the coefficients of the stress function to go to 0. So, when you go to a multiply connected object like this, you have to bring in uniqueness of displacement. And how do you identify whether the object is simply connected or multiply connected? Now, I say I have ring, this is multiply connected, you all accept. The test is you take a contour, suppose I take an arbitrary contour like this, I can shrink that contour 0 without encountering a boundary in the case of a disk. Whichever type of arbitrary contour I take on this, I can always shrink that contour to 0 without encountering a boundary. On the other hand, when I take a ring like this, suppose I take a contour like this, when I shrink it to 0, I have necessarily crossed this boundary. Suppose I cut this horizontally, I have only a specimen like this is open like this, like a C specimen, then I cannot take a circular contour like this, I will have to take a different type of contour. So, one of the tests is, if I am able to take an arbitrary contour and if I shrink it to 0, if I do not go out of the region, then that problem is simply connected, otherwise the domain is multiply connected. One simple thumb rule is, if I have cutouts like this, I have many cutouts like this, this is a multiply connected object. I have another specimen like this, is a very interesting specimen, this is appearing like Greek letter theta, so it is called a theta specimen, and when you apply compression, what happens here is, on the horizontal web it experiences uniaxial tension. This was developed by Professor Durelli for verifying some aspects of Moire, and this is a multiply connected object. So, in multiply connected objects, you have to invoke uniqueness of displacement in theory of elasticity. The general dictum is, no prior assumption on displacement is usually imposed. So, that is what is summarized here. One attempts to evaluate the displacement stress field by solving the governing differential equations satisfying the boundary conditions. So, the fundamental shift is, you solve differential equations in theory of elasticity, but even that solution procedure, you develop newer simpler methods to handle, you never go and solve a complicated differential equation, you have a simplified procedure, we will have a look at it. Usually two formulations are adopted, you have a displacement formulation, in this you find the displacements first, from displacements you move on to determining strain by invoking strain displacement equations, then finally you get the stress components by invoking stress strain conditions, and the other formulation is stress formulation. In fact, this is more popular for analytical development. So, in this you first find the stresses, from stresses you find out the strain components. For strain components you use the strain stress relations, from strain you find out the displacement, you invoke the displacement strain conditions. Here you have a catch, see, if you look at the strain components are 6, the displacement components are 3. So, when you want to find out displacement from strain, unless you bring in compatibility conditions, the displacement will not be correct. So, in stress formulation you will have to always look at compatibility conditions, they go with the solution procedure, and we look at each of these formulation, what kind of governing equations you have. We would first develop it for a 3-dimensional scenario, then simplify it for planar problems. So, in the case of displacement formulation, you can get the governing equations by combining stress equations of equilibrium with the stress displacement. So, this gives you, they are in a cyclical order, we will look at them. So, you have this as del squared u plus 1 by 1 minus 2 nu dou by dou x of dou u by dou x plus dou v by dou y plus dou w by dou z plus 1 by g f suffix x equal to 0. For each of these directions you will have cyclically this is formed. For the u displacement you have dou by dou x, for v displacement you will have dou by dou y, and for w displacement you will have dou by dou z. The basic form of the equation is similar, and here you have fx, fy and fc, and del is the very famous operator dou squared by del squared is nothing but dou squared by dou x squared plus dou squared by dou y squared plus dou squared by dou z squared. And what you will have to look at is, from mathematical point of view, I have to find out 3 unknowns u, v, w. I have 3 equations. So, I am in a position to identify by solving this, get the solution for u, v and w. Once I get displacement, go to strain and then finally go to stresses. So, the procedure is fairly straightforward in the case of displacement formulation. So, this is what is summarized here. From displacement calculate strain and then stress using the appropriate set of field equations. And what you do here is you evaluate the displacements satisfying the boundary conditions and equilibrium conditions. So, automatically the compatibility of displacement is guaranteed. In fact, the very famous finite element codes that we have, that is based on displacement formulation. One of the questions that could be asked in an interview is, where do you see compatibility in finite element formulation? You will have to simply say it is a displacement based formulation. So, compatibility is automatically satisfied. Now, we move on to what are compatibility conditions. I have already pointed out that you have strict strain components which are related to 3 displacement components. And what is the problem because of this? Determination of displacements from an arbitrary strain field may not lead to a valid displacement field. See, the problem is you have more number of equations than number of unknowns. That is also a problem. You should always have equal number of unknowns and equal number of equations. In either case, whether the number of equations are more or number of equations are less, you have a problem. And what is mentioned here is, in simply connected bodies, if I satisfy the compatibility conditions, I am guaranteed to get the displacement field from the strain field if I invoke the compatibility conditions. On the other hand, if I go to multiply connected bodies, I will still have to look at uniqueness of displacements. Compatibility conditions alone are not sufficient. I will also have to look at uniqueness of displacement field. And if you look at the compatibility conditions, 2 sets of equations could be constructed, which you may not have noticed it earlier. You can actually have one set expressing the normal strain components in terms of shear strain components and vice versa. So, on the left hand side you will have normal strain components, on right hand side you will have suitable combination of shear strain, and you will have on the left hand side shear strain components and suitable combinations of normal strain. We would look at them. In fact, you would have derived it in your earlier classes, and the set 1 looks like this, and this is also in cyclical order. On the left hand side you have shear strain which are related to normal strain components, and you have strain epsilon xy, epsilon yz and epsilon zx. And what is the condition that you have? 2 times dou squared epsilon xy divided by dou x dou y equal to dou squared epsilon xx divided by dou y squared plus dou squared epsilon yy divided by dou x squared. I would like you to have these equations in your notes, and this is in a cyclical order. If you write one such expression, following that example you could write for the other. So, if I have epsilon yz, I will have epsilon yy and epsilon zz coming in this equation, and you differentiate it with respect to z and then differentiate with respect to y here. So, when I go to epsilon zx, I have dou squared epsilon zz divided by dou x squared plus dou squared epsilon xx divided by dou z squared, and these are the conditions relating strain components, because each strain component is related to a particular displacement component. Based on that only, to emphasize compatibility of displacement field, these strain components have to be interrelated, they are not totally independent. And the other set is, I have on the left hand side normal strain component, on the right hand side you have a combination of shear strain components. And what I have here, I have dou squared epsilon xx divided by dou y dou z equal to dou by dou x of minus dou epsilon yz divided by dou x plus dou epsilon zx divided by dou y plus dou epsilon xy divided by dou z, and this equation is repeated cyclically, and you have to recognize that minus sign is related to whatever the differential here. If I differentiate with respect to dou by dou x, you have minus sign attached to that. In the second expression, I differentiate with respect to dou by dou y, so minus sign comes to the term involving dou by dou y. A similar thing you can see when you have the differential with respect to dou by dou z, you have the minus sign attached to dou by dou c. And how the components are, see, if you look at epsilon xx, I have epsilon yz, zx and xy, they are repeated, yz, zx, xy are repeated. The minus sign changes depending on the position, and you differentiate with respect to x in the first case, the second case you differentiate with respect to y, and finally you differentiate with respect to dou z. These are very standard expressions. Now what we want to look at them is, we want to look at them in terms of stress components. You know, by putting the stress components and solving it, it is a bit involved process. We would nevertheless look at the final expression, and these are famously known as Beltrami-Mitchell equations, and we would observe how the equations look like. These equations are very long, nevertheless take pains to write them down. I would read them for you. Del squared sigma xx plus 1 by 1 plus nu dou squared by dou x squared I1, where I1 is the first invariant, that is equal to minus nu by 1 minus nu dou fx by dou x plus dou fy by dou y plus dou fz by dou z minus 2 times dou fx divided by dou x. So, what you find here is this term gets repeated for all the expressions, only the last term changes. The first equation it is fx, second equation it is fy, and third equation it is fc. and this changes as sigma xx, sigma yy, sigma zz, and the middle expression everything remains similar except the first expression, it is dou squared by dou x squared, second expression it is dou squared by dou y squared, and third expression it is dou squared by dou z squared. And another aspect you have to look at, see what you have this as Fx, Fy and Fz are body forces. See, one of the important class of problems in solid mechanics is when the body force either remain constant or goes to 0. Whether it is constant or goes to 0, what way these expressions look like? If you look at very closely, suppose I take the case when body force is constant, none of these differential can exist, they will all go to 0. So, the right hand side of these expressions will go to 0. If you look at the left hand side, the equation is a function of the Poisson's ratio, you have to keep this in mind. So, the elastic constant of the material comes into play when you are looking at a 3-dimensional problem in the absence of body forces. So, I have 3 such expressions, I will have 3 more such expressions involving the shear stress quantities. They are del squared sigma xy plus 1 by 1 plus nu dou squared by dou x dou y into I1 equal to minus of dou fx by dou y plus dou fy by dou x, and these are cyclically repeated, and it is mentioned for clarity del squared is nothing but dou squared by dou x squared plus dou squared by dou y squared plus dou squared by dou z squared, and I1 is the first invariant sigma x plus sigma y plus sigma z, and F suffix I are body force per unit volume. Here again you can notice when the body force remain constant or 0, the right hand side goes to 0, nevertheless the expression contains the Poisson ratio, it appears as 1 by 1 plus nu. So, when you look at the compatibility conditions in 3 dimensions, material constant also influences the stress field, it is a very important aspect, and I hope you had sufficient time to complete writing these expressions. So, what you have is, if the differential equations of stress compatibility are solved such that they satisfy the boundary conditions, then one gets 6 stress components. You obviously have 6 differential equations to solve for 6 unknowns. So, now you have stress components, from stress components find out strain, then displacements using the appropriate field equations. See, although the governing differential equations are formulated, if you really look at the analytical approach, the number of 3-dimensional problems that are solvable are very less, and only a very few problems people have solved it in all its totality. That is the reason why numerical and experimental techniques are really necessary for solving practical problems. But what we would do is, we would look at solution to plane elastic problems. In fact, in this slide just observe the animation, you do not have to try to draw this, we would spend time on each of these special cases separately. At that time, if you draw the animation, fine. Plane problems can be solved easily than the general 3-dimensional problems, since certain simplifying assumptions can be made in the treatment. That makes your life lot more simpler. In fact, a variety of practical problems could be simplified either as a plane stress or a plane strain situation. And what is a plane body? A plane body consists of a region of uniform thickness, that is very important, the thickness has to be uniform, bounded by two parallel planes and by any lateral surface. So, what is emphasized here is the top surface and bottom surface have to be plane, they have to be parallel, it could be connected by any lateral surface, the shape could be anything. The thickness of the body must be uniform, it may be very thick or very thin. Both these cases you could identify as a simpler methodology. When the thickness is long, very high, usually the plane strain approach is used. On the other hand, if the thickness is small, plane stress approach is invoked. The key point here is loading should be in the plane xy. Now, we will take a plane stress as well as plane strain, case by case. You could now sketch the diagram. The key point here is loading should be in the plane xy, and the thickness is almost close to 0, only for convenience you show a finite thickness, in reality it is just a plane, and the moment you plane stress, everybody will ask what is a plane stress situation, define. Most of the times you would come out with the stress tensor, and you state the stress tensor as sigma xx tau xy tau yx sigma yy, but it does not stop here. See, the moment you say plane stress and planar problems, people think everything related to the problem remains in plane, that is a too strong a conclusion, you should not do like that. When you look at plane stress, the stress tensor is only in the xy plane, suppose you take that as the plane stress situation, you will have sigma xx sigma yy and tau xy, but you look at the strain quantity, it is no longer 2 dimensional, it will be 3 dimensional. And what is the strain tensor? The strain tensor will appear like this. I have epsilon xx, epsilon xy, epsilon yx, epsilon yy as well as epsilon zz. If you take a tension strip and then pull it, you would really not recognize the change in thickness that much, because the stress levels are reasonably small, the strain is going to be much smaller. On the other hand, if I have a specimen which has a crack, because of very high local stress, you will find near the crack tip a dimple would be formed. That is because of the lateral strain. Lateral strain cannot be ignored, and you have the dimple formation in the zone near the crack tip. In fact, I would show you another diagram. This is taken for a aluminum specimen. You could see here, you could see very clearly. I will enlarge this picture. I have a crack and you find a significant change near the tip of the crack, and this is how the model has been loaded, and this is a dimple. There is primarily because you have lateral strain, this cannot be ignored, that becomes very significant when I have very high stress concentration. In fact, people have utilized this as a physical feature to develop a new experimental technique called method of caustics. Normally plane stress, you look at the stress tensor and carry on with it, you do not even look at how the strain tensor looks like. That is wrong, you have to know both the stress tensor as well as the strain tensor. Not only this, I would appreciate you go and look at what is the orientation of maximum shear stress plane in the case of plane stress situation, because the maximum shear plane orientations are different in the case of plane stress as well as plane strain. When we take up modeling of plastic deformation at the crack tip, slip would be dictated by that plane only. So, you have to understand how slipping of planes can happen in the case of plane strain and plane stress. So, it is worthwhile to go and look at the Mohr circle for these cases. Now, we move on to plane strain. The moment you come to plane strain, you all know that you have to look at the thickness is sufficiently long, and another important aspect is loading should be uniform in the thickness direction. Here it is shown as direction z. If the loading is not uniform, you cannot idealize a situation as plane strain. Normally, you take the case of a roller bearing, the rollers in the roller bearing, you consider that as a plane strain problem, or if you have the dam you consider in civil engineering away from the edges as a plane strain situation. It is uniformly loaded and it is very long, and plane strain assumption is valid. Here again you should look at also the stress tensor. You should not stop with the strain tensor, and if you look at the stress tensor, that will be fully populated. You will also have sigma zz. It is not in a plane, it is 3 by 3 matrix. And what is the implication of this? See, in a plane strain situation, you would take out a slice and you want the edges to remain straight. The meaning epsilon z, suppose I have this as a z direction, epsilon z remains 0 means these two surfaces should remain straight. In order to keep them straight, you will have stresses developed in the z direction, only because of that the planes remain straight. In fact, we would look at this when we want to extend the solution for a finite body crack problem. We would study for series of collinear cracks in an infinite body. From that solution, if you want to take out a single edged crack or double edged crack, we would pause a plane and we would argue what kind of situation that should be maintained on the surfaces. So, when you look at the plane strain situation, you should recognize and understand physically the meaning of sigma zz. So, here again you go and look at what is the orientation of maximum shear stress. You must handle this problem as a 3 dimensional one. Similarly, the plane stress also look at as a 3 dimensional one. In this space, what is the plane? That is very important. Right now you go and look at and clarify your understanding. That understanding will help you to rationalize what kind of deformation takes place in the case of plane strain and plane stress situation when we are looking at the plastic deformation. And we are going to look at the solution methodology in the absence of body force for simplicity. And we have already seen what constitute the stress tensor as well as strain tensor in the cases of plane stress and plane strain. In both the cases, the number of independent stress components are only 3, because you could calculate epsilon z in the case of plane stress, you could also calculate sigma z in the case of plane strain. They are dependent on other quantities. So, the independent quantities are only 3. So, you require 3 equations to solve for these 3 unknowns. And where do the 3 equations come from? You have the equilibrium equations, they are very famous, and mind you, we have already said that we are not going to consider body forces. So, the equation reduces to dou sigma xx divided by dou x plus dou tau xy divided by dou y equal to 0. Dou tau yx divided by dou x plus dou sigma y y divided by dou y equal to 0. And we can also look at the equation of compatibility. We have already said compatibility conditions are necessary when you are having a stress formulation, and this reduces for both plane stress and plane strain in this fashion. In the absence of body force, it appears like this: del squared sigma xx plus sigma yy equal to 0. Many times you look at this equation, you carry on with it, you do not reflect what does the equation convey to you. See, I had pointed out when we looked at a 3-dimensional scenario, even in the absence of body forces, the governing equation had a material constant appearing in the form of Poisson's ratio. If you look at in this case, the governing equation does not contain any material constant. This is a very added advantage. The observation is very important, because I have been saying I am going to illustrate many phenomena in fracture mechanics by looking at results from photoelasticity. People have done crack propagation studies in photoelasticity. People also have done static experiments on mode 1, mode 2 and mode 3. As long as the problem is plane stress or plane strain, the elastic constant do not play a role. So, whatever I see in a plastic is same as what I would see in a metallic specimen. Definitely the deformations will be different. We are not talking about deformation. As long as you are concerning your attention only to stresses, for the same load both will have same levels of stress. Usually you invoke model to prototype relations and you apply a smaller load on a plastic model than what is actually happening in the prototype, but the stresses developed for that value of load is same in a metallic specimen. So, this gives a mathematical justification of validity of photoelasticity for solving 2-dimensional problems. So, you should also look at that as part of this. So, now what we will have to do is we will have to solve these equations, and how people have approached. People wanted to make our life simple. They have looked at a stress function approach. This was introduced by Airy, and this is known as Airy's stress function approach. We have to get the solution by solving the 3 equations. Instead of doing that, the problem could be reduced to a single equation by assuming a stress function phi, which is related to the stress components in the following fashion. So, you have sigma xx is related to phi as dou squared phi by dou y squared. This is for Cartesian frame of reference. We are looking at the Cartesian stress components. Sigma yy equal to dou squared phi by dou x squared, and tau xy equal to minus dou squared phi by dou x dou y. So, what we would try to show is, by just finding out phi, we would immediately get to know what is the sigma x stress component, sigma y stress component, tau x stress component. So, instead of 3 unknowns, we would modify the set of equations to determine only one function phi. The moment phi is known, the problem is solved. Once I get the stresses, go to strain, then go to displacement, and the equations are given like this: sigma xs equal to dou squared phi by dou y squared, sigma yy equal to dou squared phi by dou x squared, tau xy equal to minus dou squared phi by dou x dou y. We have already seen the compatibility condition as del squared sigma x plus sigma y. If I substitute the definition of sigma x and sigma y, how does the equation change? The equation changes to del square of del squared phi equal to 0, it reduces to del power 4 phi equal to 0, and in an expanded form this is nothing but dou power 4 phi divided by dou x power 4 plus 2 dou power 4 phi by dou x square dou y square plus dou power 4 phi divided by dou y power 4 equal to 0. So, what we have achieved is, for plane elastic problem, the solution reduces to finding a function phi satisfying the boundary conditions. We have to go and look at, do we solve the problem like this? See, we said in strength of materials you assume the displacement field and solve it for a class of slender members. In theory of elasticity we said we do not assume the displacement, we evaluate as part of solving differential equations. Then we qualified, in some cases we will have to look at uniqueness of displacement. So, multiply connected bodies are difficult to handle. Then we said we will look at experiments and look at how the displacement is, we will invoke it. We said all that. Finally, we are not looking at as a mathematical exercise. Ideally, I have to get phi satisfying this equation and the boundary conditions and solve the problem. So, I have to define the problem by specifying the boundary and evaluate phi from that, but we will not do that. What we will do this, we will follow what is known as an inverse approach. So, what do you do in an inverse approach? We will not solve the biharmonic equation and obtain phi, but forms of phi that satisfy the biharmonic equation would be investigated. So, we do it in a reverse fashion. Ideally, what I should do, for a given problem specify the boundary condition and you know the governing differential equation, solve the governing differential equation and get phi. We do not do that. We look at what forms of phi are permissible that they satisfy the biharmonic equation. Either the functions individually or in linear combinations are investigated to see what problem it represents physically. So, you are actually adopting an inverse approach. You are not solving the problem upfront. What you are actually doing is, this is the biharmonic equation, we would look at what functions of phi are valid candidates to satisfy the biharmonic equation, then we go and see which physical problem this stress function represents. So, in fact, in 1930s the research was focused on determining phi for various types of problems. The moment phi is determined, everything else is found, because once phi is known, sigma x is given as dou squared phi by dou y squared and so on and so forth. So, the challenge is in finding out what is phi. As I mentioned, we are actually looking at forms of phi in different coordinate system. Now, we take up the Cartesian coordinates, we will also look at forms of phi in polar coordinates, and phi could be a polynomial function. That is the simplest to think of. You can take different orders of polynomial that satisfy the biharmonic equation and investigate what physical problem it solves. You could also have phi represented in terms of Fourier series. See, in fact, when you are learning a first level course, you learn the bending moment diagram and shear force diagram to understand how the bending moment changes along the length of the beam. You normally take up concentrated loads, because they are easy to illustrate how a bending moment could be drawn. When you come to theory of elasticity, it is always convenient to handle a distributed loading. Concentrated loads are difficult to handle. So, when I have a concentrated load, I have to use a Fourier series and invoke several harmonics to obtain a concentrated load. So, you will find solution to 3-point bending is done in a much more complex fashion using Fourier series than a beam with a distributed loading. You learn it other way when you are learning the bending moments. And you could also find out phi based on analytic functions. In fact, in a course in fracture mechanics, we would look at analytic functions as candidates for defining the stress function. The moment I strike a goal domain, what is the stress function for a given problem, all other steps are completely known. So, the challenge lies in finding out what is phi for a given physical problem, and it is not a simple task. And if you look at, are there set procedures to find phi? The answer is only no. One may obtain it intuitively or by trial and error. So, the whole of analytical development hinges on what is the stress function phi. If you are able to find out a stress function for a given problem, the problem is completely solved. And this is the reason why people also developed different coordinate system to comfortably specify the boundary conditions. So, what we will look at is, we will take up a simple problem, we will just start the procedure and continue it in the next class. So, what I am showing here is beam under uniformly distributed load, and this is the problem usually solved in a course in theory of elasticity. We would just see the highlights, we will not get into the complete solution procedure, and we would look at what is the shear force as well as the bending moment variation. And what is shown here is what is the sign convention used. On a positive phase, positive shear is positive. Similarly, on a positive phase, anti-clockwise bending moment is positive. And for a problem like this, you will have variation of shear force like this, variation of bending moment like this. See, I have already pointed out, is flexure formula valid for this case? This question you would not have asked when you have done a course in strength of materials. You simply learned flexure formula for a beam under uniform bending moment and applied it to cantilever beam, simply supported beam and overhang beam. So many problems you have done, you have never looked at the nuances. In the last class I had shown, when I have constant shear force, then plane section do not remain plane before and after loading. In fact, it has a variation. Fortunately, it does not interfere with bending. So, bending and shear were uncoupled for normal cross section beams unless you look at deep beams. So, you are justified in extending flexure formula when shear force remain constant. And what you see here, shear force is not constant. So, bending stress whatever you calculate from your strength of material will not be accurate. From a mathematical standpoint, the solution will not be accurate, you have to anticipate that. So, you should not say, I have already solved this problem in strength of materials, why should I solve it in theory of elasticity? You would solve it by theory of elasticity and find out what are the corrections that you get, and you say, for practical situation these corrections are very small, I can still live with strength of material solution. That is different, that is okay, and that is how engineers operate. Engineers always solve a problem and bring in correction factors. In fact, we would look at from that perspective, because while learning fracture mechanics you should also have your fundamentals clear, and that is the reason why I am spending some time on reviewing strength of materials as well as theory of elasticity to bring out the nuances. So, that is the idea behind it. So, in this class we have looked at basics of theory of elasticity. I have said that you determine displacement as part of the solution procedure. So, essentially you attempt to solve differential equations. Even in that case we have segregated class of problems involving simply connected bodies and multiply connected bodies. In simply connected bodies, compatibility conditions actually guarantee for you to get the final solution while using stress formulation. In multiply connected bodies, you have to bring in uniqueness of displacement, until then the solution is not complete. Then we moved on to look at what is an Airy stress function approach. We said that it is an inverse approach. Rather than finding out phi satisfying a given problem of the boundary conditions, we in fact look at candidates for phi which satisfy the biharmonic equation, then qualify which physical problem does this phi represent. So, in that sense it is a semi inverse method. Once you get the phi for a problem, everything about the problem is known, because that is embedded in the development of this semi inverse method.